Hi friends, today I would like to explain about volatility keyword in embedded system. So this is my setup. Let's say I have a microcontroller, I'm reading a button on and off from the GPIO and I'm powering on the LED. Okay, so let's say powering on the LED. So when I pressed it, it will be read as a 1 and then the LED is on. If you don't press it, it will be read as a 0 and the LED is off, no press means. So yeah, my pseudocode is like this, reading the GPIO and switching LED on. So this is where my my code needs this volatility keyword. Why? So I've done two ways. I wrote a code without volatility keyword and it's not working. Then I suddenly realized the value of the volatility keyword and it started working. How? So let's see the code part and assembly part of that code. We will get more details about it. Yeah, now let's say we are using the keyword version of the code. It performs very explicit memory access from memory mapped hardware. In case of non-volatility version of the code, meaning the local value will be cached and hardware address may be missed, meaning the changes at the hardware will be missed. So we just see how the code will be operated. Let's say assume the GPIO connected here, LED connected here, like button here and LED connected here. So in this case, in means button reading, out means LED. So yeah, I'm writing this entire in the while loop where I'm getting volatility read from the button and I'm checking the condition here. Once my condition satisfied, then I am again it's a volatility write. So like this my code. So the next part of the code which is non-volatile. If you see the keyword which is here, no volatile. But in the previous section you see I have a volatility keyword. Okay. So this is the major difference. So but the code is same, nothing differs. But how it will impact our operation. So let's say you builded this code with optimization O2. Okay. Optimization O2. Let's say you build it with this code optimization O2. So the version of the code will be like this in the assembly level. Okay, so yeah, you can understand these are basic things. We are updating a link register. It is 14 number in R. So this is like next where to jump, like where to came from. So it's a stack operation push. Then this is where our loop starts. So first it is our GPIO in address. We are storing in L1 and then we are reading it from the L1 address. This is the read from the address which is located in the R1, so it's a load instruction. So we are writing into R2 and we are performing the operation again. You see this is for the GPIO out axis. Again we are keeping in R3, comparing R2 with 0. Okay, if not some operation, again some operation. See, this is where we are storing volatility read. So if not equal, then different case. If equal, we are updating with R4. So you see this is exactly what that means, completely from the memory. You're nowhere reading it from the cache or the local register. Whereas another case where we do not use the volatility keyword, then you see the assembly code part of it. So here again this stop command, just to understand this push operation to for the next functional function pointer, and then LDR again see load instruction with in address, and we are reading this value. This is a read once, meaning we will see it. So and this is under operation again. See, you see the loop catched here, meaning we are storing the value R2. Okay, so compare with R2, and this is 4, and see you're always comparing with R2 here. and this value is stored in R2. You only read once. After that, you see we are now updating this. You are in this loop every time. You only comparing with R2 which is already loaded once here. And then if it is comparison happen by the time it is 0 or 1, then only here always either 0 or 1 will be reflected and this loop forever. If it broke, then it will happen anyway. It's a while one, so it won't broke. So you see, this is without a volatile keyword. So this is why I lost the operation without a volatility. Always I'm reading from the R2 register of the ARM. But whereas my previous code, it is always, see, there is no catchy. If you see my code, always my loop start here. Always I'm reading the live value into R2 and comparing R2. So this is where the volatility came into picture. So to understand better now, I would like to explain more about this. See, the volatility keyword come into picture in two cases. One is memory mapped IO address access, probably our hardware GPIOs, something like peripherals and all. And other one is like hardware register read, meaning let's say you want to read status of the hardware. For example, let's say you are waiting for the SPI peripheral or I2C peripheral or UART peripheral something. You are expecting some status. You want to read it from the which hardware address which is belongs to this status. So then only you have to perform some job here. Let's say. So in that case, you should use this volatility keyword. Otherwise, your operation will not perform the actual results. So this is where the volatility keyword plays a role, and you have to understand when to use and when to not, because it costs you extra cycles. Extra cycles mean like you're catching if you're using the volatility means your more code will execute. More code means more cycles. Why? Because you are always requesting your memory access always from the memory access. Okay, access always from the memory, so it gives you some extra code and exam some penalty on the cycles, but it's required. Yeah, so that's all, friends. If you have any questions, please comment below. Thank you.